So in this video, I'm going to explain how to do basic projectile motion. We're going to start off with the notes. On any projectile motion problem, step 0 is to break it into a horizontal and vertical problem. X will deal with anything in the horizontal direction. Y will deal with anything in the vertical direction. Next step is to determine what type of problem it is. There are drop problems, that's one category, throwdown problems, and then there are 3 different types of throw-up problems. It's a drop problem if your initial velocity in the y direction is 0. Your horizontal velocity can be anything. And the velocity in the vertical velocity time graph will always look like this. It will start at 0. It'll have a slope of -10. And as time increases, the velocity drops. And the area inside that triangle will be how far it's fallen. The most important equation in this problem is going to be delta y equals -5t squared. In the next section, your initial velocity is going to be less than 0. So if you have a negative velocity, that would be considered a throwdown problem. On a throwdown problem, it starts below 0, and it gets more. It'll have the slope of -10. And the most important equation in this one is y final equals -5t squared, plus your initial velocity in the y direction times time, plus y initial. The problem with this formula is a lot of times you have to use the quadratic equation, which I dislike, so I don't use it very much. And then the third type of problem is a throw-up problem. And with that, your vertical velocity is going to be greater than 0. So if your vertical velocity is greater than 0, you're going to have a part of it going up. And so normally you have an initial velocity at some angle. And so we have initial velocity at some angle, and we have to break that velocity up into its 2 components, the initial velocity in the y direction and the horizontal velocity. In the y direction, if I take my initial velocity times the sine of theta, that will give me VIY. And Vx will be the initial velocity times the cosine of theta. So an example is if you have a 20-second object launched at a 32-degree angle, I would take 20 meters per second times the sine of 32, and I get a velocity of about 10.6 meters per second initially in the y direction. The horizontal velocity would be 20 meters per second times the cosine of 32, giving me close to 17 meters per second. Now the reason that the vertical velocity has an I in it is because that velocity is constantly changing. In the x direction, the velocity stays constant the entire time. So the vertical part deals with constant acceleration, the horizontal parts deal with constant velocity. There are 3 other specific types of throw-up problems, throw-up A, B, and C. And let's look at the pictures of what those look like first. Well, look at all the pictures. So a drop problem, and it's going to look like half of a parabola. It will start at some height, and then it will swoop down to get down to the horizontal, or to get down to the ground. It doesn't matter what the initial velocity is in the x direction, like this one's going faster in the x direction, but it's still going to look like that. Each of these graphs these aren't really graphs, these are just a picture of what's going on with the motion. So that's what a drop problem would look like. A throwdown problem looks similar, except it's not really flat at the top. It would start with an already negative slope at the very beginning. And again, you can have different initial velocities giving you different negative parts of a parabola. Okay, and then we have 3 types of throw-up problems. We have a throw-up A problem, where it starts and ends at the exact same height. And so this would be one example. Or if you throw it at a higher height and it still comes down to the exact same spot, as long as it starts and ends at the exact same height, we call that a throw-up A problem. A throw-up B problem will end at a higher height than you started. So on this one, It starts off, it goes up a certain amount, and then it hits some position. I call it throw up B because it's like a basketball. When you shoot a basketball, you're trying to go into the goal, and the goal is at a higher height than you initially are. So a throw up B would be considered a basketball problem. A throw up C problem would be, I think of a cliff. You're standing on top of a cliff and you throw something. Part of the time it's going to go up, and then it's going to spend more of its time going down. And you can launch them from different heights. As long as you start at a higher height and you end at a lower height, a throw up C problem. Looking back at the graphs, the